Morning. After the dinner last night, I guess that it's somewhat hard to resume the meeting, but anyway, it's my pleasure to begin this session with the first speaker today, Pengzi Miao. He's going to talk about minimal hypersurfaces, isometric embedding, and manifolds with non-negative scalar curvature.
Thank you for the introduction. First of all, I'll thank the organizers for inviting me to come to the meeting. Oh, okay. Yeah, I want to sincerely thank the organizers for inviting me to the meeting. This is a very pleasant event that I'm grateful to take part in. The main theme of my talk today is about manifolds with non-negative scalar curvature. The other two subjects, minimum hypersurfaces and isometric embeddings, are related to the particular problem that I'm going to talk about. First of all, why manifolds with non-negative scalar curvature? The motivation for me is that if you take certain space-like hypersurface in a space-time satisfying certain energy condition, then the induced remaining metric on the hypersurface will be a metric with non-negative scalar curvature. And when the manifold is non-compact, say if the manifold is asymptotically flat, one has the famous positive mass theorem. So in this case, one has the remaining positive mass theorem. And if you allow the manifold to have a horizon boundary, which are the outermost minimum surfaces, and one has the remaining Penrose inequality, and these are the fundamental results regarding manifolds with non-negative scalar curvature, which are non-compact. In this talk, I'm going to focus on manifolds which are compact and have boundary. Now, physically speaking, one wants to think those compact manifolds with boundary to be part of a non-compact asymptotically flat manifold. So in other words, you can just think the manifolds I'm going to talk about next as a finite domain inside such an asymptotically flat manifold. Why I'm interested in these manifolds? That's again related to these two fundamental results. When the manifold is non-compact, assuming the end is asymptotic to the Euclidean space, then one can define the total mass of such a manifold. The remaining positive mass theorem says the mass is greater than or equal to 0, while the remaining Penrose inequalities relates the mass to a quantity coming from the area of the boundary. Now, from a physical point of view, one would like to understand if you just focus on part of the region of such a manifold, what would be the contribution of such a finite piece to the total mass of the manifold? And that's related to the so-called quasi-local mass question. So that's the motivation for the problem that I'm going to talk about. I will start with a theorem due to Xi and Tan in 2002. their theorem is the following. Consider a compact manifold with boundary, say omega of dimension n plus 1. Okay, we assume this omega is a compact manifold with boundary. So here is a picture. And in this talk, we use n to denote the dimension of the boundary. So the manifold omega will be n plus 1 dimension. And one also allows the boundary to be disconnected. In which case, we can label the boundary component, say sigma 1, sigma 2, etc. And we are going to always assume that the manifold has non-negative scalar curvature. Say R, scalar curvature. Is always assumed to be non-negative in this talk. And for the results to hold, we are going to always assume that the boundary has positive mean curvature, which means the mean curvature vector on the boundary will always point inward. Okay, now under this assumption, one wants to draw a statement regarding the boundary geometry of such omega. And to do that, one wants to compare it with a zero energy background or a reference space. And to formulate such a condition, here comes the final assumption that's in this theorem. So one would assume that, say, each boundary component is isometric. Say, assume each boundary component is isometric to a convex closed hypersurface in Rn plus 1, because omega is of dimension n plus 1. Right? So the extra assumption here is assume each boundary component is isometric to a convex, sigma I is convex in Rn plus 1. So here I will change the index 1 to I. All right, under these assumptions, the result of Xi10 is the following. Then, in this physical manifold, omega g, one has the mean curvature of the boundary. So, say, at this boundary component, we have this mean curvature function. And we can consider the integral of h along sigma I. So that's the total mean curvature. And in this target space, where we assume that sigma I is isometrically embedded in Rn plus 1, its image also has its mean curvature, which we will denote it by H0. And because one assumes that sigma I is convex, we know this is also a positive function. So one can also consider the total mean curvature of the surface in the Euclidean space. And the result is one has a comparison theorem regarding these two total mean curvature. And moreover, if equality holds, when equality holds for one boundary component, and that occurs only if the boundary is connected and the whole manifold is isometric to the domain bounded by the hypersurface in the Euclidean space. Okay, let's denote the region bounded by sigma I by omega 0. Okay, as you can see, this is a theorem of the following nature. It starts with a compact manifold with boundary, with non-negative scalar curvature. Under suitable assumptions on the boundary, one can make a conclusion regarding the following quantity. So in other words, one can rewrite Shitan theorem as the integral of h0 minus h along sigma I is greater than or equal to 0. And moreover, equality holds if and only if the manifold is isometric to part of the Euclidean space. So in this sense, one may think of this quantity, which is defined purely in terms of the boundary geometry of omega, as certain quasi-local mass quantity. Indeed, in the relativistic literature, after normalization, this is known as the Brown-York quasi-local mass. So back in omega g, there is no assumption on the second fundamental form. The assumption is assumed. So the assumption in their original result is assuming that the boundary is isometric to a convex hypersurface.
Is that convex, strictly convex?
Yes, strictly convex.
Yeah. If it's flat, you get 0 on the right side.
If it's flat, you get 0 on the right side. Yes. Yes. But later, so after this result was given, then there are in higher dimension. This assumption can be replaced. Can be weakened, say, to star shape with only H positive, mean convex. There are other remarks that one can give regarding this theorem, but I will postpone the remarks later because I'm going to introduce a problem that we are going to consider, and then I will present all these remarks together. Okay, here, to motivate the question that I'm going to discuss next, let's look at the picture in which omega has more than one boundary component. Now, because we are assuming the mean curvature vector point inward at each boundary component, whenever you fix a boundary component, say this one, then by minimizing area among all surfaces which enclose a region with this fixed boundary component, then one can always find a minimum hypersurface, say Si, which bounds a region with the chosen boundary component, sigma I. Say the region between sigma I and Si is denoted by omega I. And such a region has the property that there are no other closed minimum surface in this omega I from the way that one constructs this Si. Now, in this connected boundary case, you can also come up with scenario where you can find such a region. Say, there are pictures even in the connected boundary case where you can also see such a region, of which I will call it omega tilde. And such a region has a property that is bounded by the original boundary sigma and a minimum hypersurface. Moreover, you cannot detect other closed minimum hypersurface inside. Now, a question one can ask is, still in such a scenario, how would such a minimum hypersurface, if one like, one can call such a hypersurface the outermost minimum hypersurface relatively to the given boundary component in omega g. So how does such an outermost minimum hypersurface affects the boundary geometry of the chosen boundary component? Now, this question has a relativistic motivation. Because in a relativistic setting, a minimum hypersurface, at least in the time symmetric case, would correspond to the apparent horizon of a black hole. Say if we go to the setting of the Riemann Penrose inequality, the Riemann Penrose inequality says exactly, give us exactly an inequality which bounds the total mass in terms of the horizon area from below. So therefore, if we just stay within the setting of the Riemann Penrose inequality, here is the question. Instead of going to infinity of the manifold, we can just take a compact piece, omega, with a component, sigma, and we ask, how does the area of the apparent horizon affects the geometry of such a hypersurface? The remaining of my talk is going to be devoted to analyze this question. Okay, the theorem I'm going to talk about is a joint work with Siyuan Lu. And from our previous discussion, you already see that the basic object of study here is a compact manifold with boundary, which I will represented by this single picture. Here we have a compact manifold with boundary with non-negative scalar curvature, such that its boundary component is a disjoint union of two pieces. Where we will use sigma h to denote, where sigma h consists of minimum hypersurfaces. So sigma h is minimum. And the other boundary component, which one can call it the outer boundary component, a boundary that lies at the outer position, is assumed to be, say, topologically a sphere, and geometrically we assume it has positive mean curvature. The sigma O is topologically and we assume the mean curvature of sigma O is positive. Again, that's to say that the mean curvature vector points inward. And there are no other closed minimum surface in omega. In the physical point of view, if the boundary in this picture represents the outermost, the apparent horizon of the black hole, then there are no other, then there is no horizons that lies outside the boundary. So therefore, in this compact case, one also assumes that there are no other. Okay. Now, given such an object, the question is how to investigate the effect of this outermost minimum boundary on the other boundary component. Well, going back to Shitan's case, I think here is a remark that I'm going to. It's a rather important remark. Shitan's theorem is proved using the Riemannian positive mass theorem. Even though the theorem of Shitan appears like a comparison result in Riemannian geometry, so far the only known proof is via the positive mass theorem. Moreover, assuming the result is true, this result can be shown to prove the positive mass theorem. So assuming this is true, then one can derive the fact that the mass of an asymptotic flat manifold is non-negative. So therefore, the Riemannian positive mass theorem is equivalent to the theorem of Shitan. On the other hand, because the proof of this theorem makes use of the positive mass theorem, it does not detect, or it does not see the fact that you have a minimum hypersurface SI here. So therefore, this theorem itself did not provide us information regarding SI. Now, in order to draw such information coming from SI, one wants to compare the given compact piece into a reference space, which instead of is the Euclidean space. Naturally, one wants to look at the model which corresponds to the Riemannian parallels inequality, which is the so-called Schwarzschild manifold. So here is an assumption corresponding to the assumption in Shitan's case, which says the boundary is isometric to a convex surface in Euclidean space. So assume the outer boundary sigma O is isometric to a surface, to an sigma, where sigma is a hypersurface in a Schwarzschild manifold. So here, our target or our reference space, which I would denote it by M, n plus 1 sub M, G bar. And this is the spatial Schwarzschild manifold with mass M, which analytically has the following expression. Where sigma is the standard metric on the sphere. All right, so naturally, one would like to impose such assumption that the outer boundary is isometric to a certain hypersurface, sigma in a Schwarzschild manifold. Now, how suitable is this sigma is to satisfying we are going to list a few properties that will allow our discussion to proceed, to continue. So first of all, we are going to assume that this sigma is a star shape. And second of all, we are going to assume that this sigma is too convex. So far, this problem is proposed in an arbitrary dimensional setting. So the convexity we use on the target space, on the target hypersurface, is too convex. Now, what does too convex means? I.e., sigma 1 is positive, sigma 2 is positive. Now, what's sigma 1, sigma 2? The sigma k is the case elementary function of the principal curvature. Of sigma. So in particular, sigma 1 would be the mean curvature. So that's a convexity assumption imposed on sigma. And moreover, we need an extra assumption. That is, we want the Ricci curvature of the ambient metric G bar evaluated along the normal direction. We want it to have a sign. Now, notice that when m goes to 0, the Schwarzschild manifold limits to the Euclidean space. In the Euclidean space, the Ricci curvature is identically 0. So in that sense, this third assumption is not indeed that strong. In fact, I'm going to explain in detail why, how these three assumptions are needed. At this moment, let me write down the conclusion. Then, okay, our goal is to say something regarding the boundary geometry of this outer boundary component. So, first of all, we have a number m. M is the mass of this reference space, and we have an integral of hm. Hm represents the mean curvature of this hypersurface in the reference space. So hm is the mean curvature of sigma. And now we have a weight function n. N is explicitly given by the square root of the denominator of this warping factor, which has a relativistic meaning itself. And this weighted total mean curvature normalized by n times omega n, where omega n is the volume of the standard sphere. Now this quantity will be greater than or equal to a quantity that comes from the area of this horizon boundary. Really, it's the 1/2 of the area radius. So the volume of the horizon boundary divided by omega n raised to the power n minus 1 over n. And then plus the corresponding integral taking place on the outer boundary. Okay, here h is the mean curvature of sigma O in omega g, and then there is the weight. Now, even though I will write the weight still as n for simplicity, here n really should be thought as the composition or the pullback of this function n, known as the static potential on Schwarzschild, back to the outer boundary via this isometric embedding coming from the assumption. This arrow is our assumption. Assuming sigma O is isometric to such a hypersurface, then the function n, which is the static potential, can be pulled back to sigma O, and that gives us the weight in this quantity. So the pullback. And moreover, if equality holds, ideally, one would like to prove that the equality holds if and only if this part is isometric to the region bounded by sigma and the horizon. But technically, that could be known if a so-called Riemannian Penrose inequality with corners along a hypersurface can be shown to have the desired rigidity. So far, we cannot prove that. The conclusion we have is an equality holds if this mass parameter of the target equals the quantity comes from the horizon area, and the two mean curvature functions identically agree, which would be which are sufficient in some application itself. All right. At this moment, I think a natural question is, do you have examples? Do you have examples of such omega g where your assumption is satisfied? And that's given by a related theorem. So if you start with an asymptotic flat manifold, well, in this case, I need to focus on 3 dimension. So if you consider a 3-dimensional asymptotically flat manifold, which I do not have, which I really didn't define. If you consider a large coordinated sphere, say this SR, consists of points whose coordinate length is a fixed number, then as R large enough, then for sufficiently bigger R, such a hypersurface can be isometrically embedded into any Schwarzschild manifold with positive mass. So the claim is for sufficiently large R, there exists such an isometric embedding. Satisfying all the assumptions. That's all these 3 assumptions. Moreover, one can show that a quasi-local mass type quantity coming from this inequality has the property that it goes to the total mass. So moreover, if you take M of the target space, M, plus 1 over NWN times the integral, well, in this case, N is 2. So this normalizing factor is just A pi. integral of hm minus h times n, then such a quantity can be shown to limit along this particularly given isometric embedding to the total mass of this asymptotic flat manifold. So this is a remark. You may view this as a remark or a supplement to the result that we just stated. I will not have, it seems I don't have time to go through the detail of the proof, but I do want to mention an application of this inequality. Since my talk has a subject called isometric embedding, in the remaining 5 minutes, I do want to comment on the isometric embedding part. Okay, now, a main advantage, a main feature of Sheet-Hand theorem in dimension 3 is that as long as the boundary component is assumed to have positive Gauss curvature, then by the solution to the value embedding problem, such a boundary automatically admits a isometric embedding into R3, which is unique up to the isometry of the ambient space. In particular, this quantity is geometric. The right-hand side of this inequality in Sheet-Hand's theorem is geometric. It does not depend on the isometric embedding because it's unique. On the other hand, it's a very recent result of Chunhe Li and Zhizhang Wang. So it's a theorem of Li and Wang, which says there are metrics on the two-sphere which allows different isometric embedding to the Schwarzschild manifold. Indeed, a special case of the theorem says even the standard metric on S2 can be isometrically embedded in a different way to a Schwarzschild manifold. Now, if the metric is round, obviously you have a standard placement which places the round metric into a rotationally symmetric sphere. On the other hand, they show that there are other embeddings, which is produced even in a perturbation fashion. So one can perturb such a round sphere in an isometric way so that you get a different isometric embedding of this round sphere, which we will denote this non-spherical image by sigma 1, and we'll devote the round image by sigma itself. Okay, now here the application of this theorem is we can apply this inequality to the domain, say, bounded by sigma 1 and this horizon. Let's call this omega 1. So assuming, suppose you start with these two isometric embedding, one is round, and applying the inequality to this omega 1, so what do we get? We would get m plus, in this case, it's a quantity that comes from the Brown-Yoke mass, which is 1 over 8 pi times the integral of this mean curvature, which is h. Well, my notation is a little bit not consistent. Okay, let me write it as hm. Then times the static potential on this round sphere. This is greater than or equal to square root of the area of sigma h divided by 16 pi plus 1 over 8 pi integral of h, where that's the mean curvature of sigma 1. So let's write h as h1. Then times the pullback of the static potential. Here, notice that we are comparing these two hypersurfaces in the Schwarzschild manifold, right? Because we are assuming a round sphere can be isometric differently. Therefore, those two hypersurfaces have isometric. Therefore, we apply this theorem. Now, let's look at this inequality. This mass parameter equals the quantity that comes from the horizon, because we are doing everything on a same Schwarzschild manifold. So these two numbers are the same. Now, for this standard isometric embedding, the static potential function n is a constant on the round sphere. Therefore, its pullback is a constant too. So therefore, those constant drops. So here we end up with the conclusion that even though the isometric embedding of a round metric into a Schwarzschild manifold is not unique, however, the standard embedding is characterized by an inequality which says the total mean curvature is maximized by this standard isometric embedding. And moreover, if equality holds, then using the equality conclusion here, the equality holds if and only if the two mean curvature agree. In this picture, that says that if the equality in this total mean curvature comparison holds, then the mean curvature of H1 must be the mean curvature which is HM. But HM is a constant, as it's the mean curvature of this rotationally symmetric sphere. Therefore, sigma 1 has constant mean curvature, and one can resort to a theorem of Brundle, which says the only CMC surface in a Schwarzschild manifold must be rotationally symmetric. So in other words, that says the standard embedding of a round sphere is characterized to be the unique maximizer of the total mean curvature. I think I'll stop here.